Hi guys. So today we're going to talk about lists, which is in chapter 15, again, if you're following in the book. So we've talked about some of these, in a way, we've talked about linked structures and we talked about lists. We're going to go into a little bit more detail. We're going to look at the list abstract type. So not just, implementing other things using lists, but, how to implement the list structure itself. Because sometimes, we need a list and we don't want to implement a stack or a queue or any of these other things. We just want to use a list. So let's look at the list abstract data type on its own. And so in this chapter, we're going to talk about some of the types of list collections. We're going to look at how you can use lists to solve problems. We're going to look at some list implementations, and we're going to compare some of the list implementations. So in this video, we're basically going to talk about, so we're going to start with lists. So a list is a linear collection like a stack or queue. It's a lot more flexible. So the things that you were building your stacks and queues out of were actually lists in the way that they were built. It was a type of list. So the abstract data type, so we have to sort of differentiate between those implementation and then the abstract data type. So the abstract data type, remember, is like the interface. And there are many different ways to implement the interface. So it just happens that linked structures, so linked structures and lists sort of historically were kind of the same thing. Like when I took data structures, they were considered sort of the same thing. And now they sort of abstracted out and they say, okay, well, these are lists, but you don't have to implement lists this way. List as an interface. They want to have a sort of a homogeneous view of how these things work. So there's interfaces and there's underlying implementations. The interface is called the ADT, the abstract data type, and then the implementation is something else. And you actually can implement lists in different ways, and we'll look at those. But basically, a list is a linear collection. So adding or removing of the elements of the list can occur at either end or anywhere in the middle. So if you think about some of the linked structures implementations that we looked at, you could actually implement, you could actually stick things in the middle anywhere you wanted to put them, right? They don't have to be at the beginning or at the end. They could actually insert them in the middle. And even the array implementations, you could implement lists as arrays, and those things you can stick in the middle. You just have to shuffle things around. It's not an optimal implementation for a list, because when you insert things in the middle of an array, of course you have to shift. And if you have to shift, that means an insert is order in, right? Because you have to shift things. So let's look at three different types. We're going to look at ordered lists, unordered lists, and indexed lists. So the elements in an ordered list are ordered by some inherent characteristic of the elements. For example, the names, the scores, the employee number. There's something that you're using to order the list. So the elements themselves determine where they're stored in the list. So here's an ordered list. And you see we have the front, we have the back, and we're going to insert this 54 in the middle. All right, so we have to think about here, we're going to go back to our analysis of algorithms discussion, right? We're always going to go back to analysis of algorithms when we're looking at these things. And we have to think about an ordered list. So when we looked at stacks and queues, right, we used lists in some cases. We use these linked structures like lists to implement our queues, but we always inserted at the beginning and the end, right? So if we have an ordered list, let's say we've implemented it. So this is the abstract view. This isn't a particular implementation. This could be implemented as an array. It could be implemented as a linked list, right? A linked list. So let's assume that we have an ordered list and we want to look at doing an insert in an ordered list. What is the big O of doing an insert in an ordered list? So you might initially think to yourself, oh, well, we just got to swap a few references around, right? We make this thing point to that thing and that thing point to this thing, and it's all good, right? Provided we have a linked list implementation. But in fact, that's not correct, because the first thing that you have to do when you do an insert in an ordered list is figure out where you're supposed to insert it. So first, you have to search through the list for the right location for that element, because this is an ordered list. We can't insert things anywhere. It's in an order. And so we have to start at the front of the list and we have to search all the way through the list until we find the spot that this thing is supposed to be inserted. And that is an order in operation. Now the actual insert itself, the manipulating the references, that's order one. So On average, inserting things into an ordered list with a linked list implementation is big O of n, because it takes us big O of n operations to find where we want to put it. And then once we find out where we want to put it, it only takes us big O of 1 to put it in that spot, right? All right, now let's go back and let's think about if we implemented an ordered list with an array. So if you implement an ordered list with an array, you still have to find the location, right, that you're going to put it. You have to search through the array one by one by one until you find where you're going to put it. And on average, you're going to find it about halfway in the middle, right? So it's going to be n over 2, which is big O of n. So it's going to take us n over 2 operations to find where we want to put it. N over 2 compares. Now, once we find where we want to put it, we have to shift things in the array, right? Because the array, we can't just insert in a location. There's something already there. If we want to put something in there, we got to shift everything up. So that shifting, if on average we find it in the middle, then it's n over 2 shifts, right? Because you shift the first one up, the second one, the third one, the fourth one, all the way up to n over 2, right? So on average, it's going to be n over 2 shifts to actually do the insert. So that's n over 2 to find it, and it's n over 2 to insert it, right? So what's the overall cost of doing this, right? It's n over 2 plus n over 2. So it's order n. So an insert in this case takes order n operations, right? So inserting in a linked list takes order n operations. Inserting in an array list takes order n operations, but inserting in a linked list actually takes, it's more efficient. They're both still big O n, right? So you got to think about these things when you're thinking about these inserts. When you're doing ordered lists and you're trying to put it in a certain spot, you got to find where you're going to put it. Even though the linked list implementation, you may think, well, I don't have to shift anything around. That's true. You just have to swap 2 or 3 pointers. 2 pointers, right? If it's a singly linked list, you swap 2 pointers or 2 references. It still takes you n over 2 on average operations to find it. With an array, it takes you n over 2 average to find it, and then it costs you n over 2 more to shift. So because those aren't done in loops, right? It's not n over 2 times n over 2, because we're not shifting. If we had to shift every time for every search, that would be n over 2 times n over 2. But because we're finding and then we're shifting, it's n over 2 plus n over 2, which is, it's still order n. So they're both order n implementations, but the linked list is faster, right? By an order of 2. Although it may cost you more to traverse it. So hard to say, right? All right, so we talked about order lists. Insert is n over 2. Removing from an ordered list, same thing, right? You got to find the element that you want to remove, which means you have to search through the list to find it. Once you find it, you have to remove it. So it's n over 2 on average to find it in an ordered list, and then constant time to remove it. So overall, it's going to be order n to remove. So we have to think about these things. Ordered lists are slightly different than stacks and queues. Stacks and queues, we always knew where to put it. We put it in the front, we put it in the back, right? One of the two. And that's an order 1 operation, because we know where to put it. But with an ordered list, we have to find where to put it, or we have to find the element that we want to remove. And both of those operations, both of those finds, require us to traverse the list. There's no other way to jump around. We'll see some data structures that lets us find things much quicker than that. But with a list, you basically have to start at the front and you just search until you find it, one after the other. And you find it halfway in the middle on average, which means that's an order in operation. So think about these things when you're looking at these data structures. We have to consider these things. It's questions on the test, right? So order in to assert, order in to remove for ordered lists, right? All right, let's look at unordered lists. So an ordered list, so there can be how can I say this? There is an order to the elements in an unordered list, in the sense that they are sequential, right? They're linked together. Think about the linked list implementation or the array implementation. They're in an order from one, from element 1 to element n at the end. but that's not based on element characteristics. So we're not sorting them based on a name or whatever. They're just in there in some order that's random. So the user of the list can determine the order of the elements. And a new element can be put in the front or the rear or inserted in after a particular element already in the list. So it can be basically, you can put it anywhere that you want to put it as a user. So unordered lists look like this. We can add an element at the front. We can add an element at the back. Any place we can add an element in the middle. So in this case, we have to think a little bit more because it's a little bit more difficult to do the analysis of what's the cost of an insert, what's the cost of a remove. It depends. This one is not straightforward. If our policy is, well, we don't care about the order of the list, we're always just going to put it in the list in the front, or we're always just going to put it in the list in the back. That's an order in operation. If we're going to go through and choose which element we're going to put it or where we're going to put it, and that's how we plan to do our inserts, then that is order in square, or in, sorry, not in squared. That's order in, because we have to find where we want to put it. Now, the actual insert, the insert call itself, once you find where you want to put it, that is order one, right? We just have to swap a couple of, unless it's an array. If it's an array, then we have to shift, and that's an order in. So if it's a link structure, the actual insert, the sticking, once we find it, where we want to put it, that insert costs is order one, right? But finding where we're going to put it, that's order in. So the implementations are going to have an effect on that, right? So let's say our policy is to put it in the front of the list. We're always going to put it in the front of the list. If we have a linked list implementation, we put it in the front of the list. That's an order one operation because all we have to do is stick it in there, right? On the other hand, if we have an array implementation and we always want to put it in the front, if we define the front as the 0th element in the array and the rear as the nth element in the array, then what we have to do to insert it at the 0th element is we have to shift everything down. That is order in because we have to shift in elements, right? On the other hand, with an array implementation, if we want to put it on the end, we don't have to shift anything, right? But if we delete something, depending on where we delete it from, the point being that you really have to think about these things. You really have to think about the case, how is it being used. When you're picking your structure and you're deciding what your underlying implementation needs to be, you have to think about exactly how you're going to use it because that determines the order, especially for an unordered list. So it's a little bit weird when you pick these things when you're trying to decide what the order is going to be of them. All right, so an index list, the elements are referred to by the numeric position in the list. Like an unordered list, there's no inherent relationship between the elements. The user can determine the order, and then every time the list changes, the indexes are updated. So an index list probably would be implemented with an array because if you're doing an index, I mean, let's think about the different ways we can implement this. If we want to implement an index list and we want to use a linked list structure, right? If we want to find the 5th element, we just have to traverse 1, 2, 3, 4, 5, right? That takes us, its own average, if we look at the time it takes to find any index in the list, the average cost is going to be an over 2. So finding a particular index, just doing that lookup by index, is going to be an order in operation, right? Because we've got to find it in the list. On the other hand, if your indexes list is based on an array implementation, we can just use the array index, right? If you want to find the 5th element, that's just array bracket 5, close bracket, right? So the implementation underlying and the operation that you plan to do with it has an effect on the order of the operation that you plan to do. You have to think about these things when you're designing it because this is very important to consider because it can have a very large effect, right? All right. So here's an index list. Our list elements are indexed 0, 1, 2, 3, 4, 5, 6, 7. Adding an element, again, you know, here's the trade-off. If we have a linked list and we want to find it, and we want to insert, well, what does it cost? Let's say we're going to add an element in the middle with a linked list. What does it cost? We got to find the middle first. Let's say we want to put it between 3 and 4. We start at 1 or 0. And then we go to element 1, 2, 3, and then we're going to insert it after 3, right? So it took us, on average, for any spot in the array in the list, it's going to cost us on average n over 2 to find the spot. But then once we find the spot, the cost to insert is just constant, right? Because we just swap 2 references and we're good to go. On the other hand, if we implement this with an array and we want to add an index we want to add an element in the middle, the cost to find it in the middle is constant, right? Because we know where element 3 is. But we have to shift all the elements above it up 1 so that we can stick it in that slot. So the cost to do the insert, the finding part is order 1, the shifting part is order n. So it's still an order n operation. So again, you have to think about these things. You have to think about the implementation. Some of the answers sometimes to what's the big O of doing X is not as straightforward as it is with the stack or with the queue, okay? So you're going to have to think about this a little bit with the lists. It's thinking time. So, all right. So in the Java API, the list classes primarily support the concept of an index list and somewhat an unordered list. So the API does not have any classes that directly implement an ordered list. The array list, which you've already seen, and the linked list classes both implement the list interface. And again, it's a generic based interface, right? So here are some of the operations from the list interface. There's actually quite a few. Like I said, there's this is sort of the canonical, well, there's the canonical list operations, and then there's the ones that people do because there's lots of stuff you like to do with lists that is not canonical. So we can add an element. We can add an element at a specific index. So add an element adds to the end. We can insert a specific index. We can return the element at a specific index. We can remove the element at a specific index. We can remove a particular object. We can set, which means replace the element at a specified index. Or we can ask how many elements are in the list. And again, you can go down through these things and you can think to yourself, all right, well, depending on how I implement this, if it's an array list or it's a linked list, what's the cost of doing all these things? And you know, the answer depends, right, on which implementation you have underneath it. So that's the end of this lecture. Thanks, and join me for lecture 2.